Hello. Today I wanted to talk about an integral which looks pretty intimidating at first. You've got a reciprocal, you've got an arbitrary power of tan in the denominator, and yeah, it's hard to know where to start. But um, this is actually an example of how we can consider even and odd functions, and how when we've got a definite integral like this, we can actually find the answer without finding the integral, without evaluating the indefinite integral. So yeah, first things first, I'll talk a little bit about integration in general. So an integral from a to b will find the area bound by a function and the limits that you impose, the x-axis a and b. Um, in the case of even and odd functions in integration, um, they're most useful when you've got symmetric bounds. So when a equals minus b, meaning that the distance from the origin to the positive x-axis, your positive x bound and your negative x bound are the same. So in the case of an even function, where f of x is equal to f of minus x, so we've got complete symmetry, everything on the positive x-axis is the same as the negative x-axis, we can just see by inspection that an integral from 0 to b is going to be half of the integral from minus b to b. So it's a small simplification, doesn't help much, but it kind of leads us on to other useful things. So for example, for odds, where f of x is equal to minus f of minus x. So, for example, a sine function where we've got complete anti-symmetry, we see that if we take the integral from 0 to b, it's going to be exactly negative to the integral from minus b to 0. So the total integral from minus b to b is going to be 0, no matter how complicated the function is. If we can show that it's odd, if it satisfies this f of x is equal to minus f of minus x, then we can just say it's 0, which is useful. So we've seen how considering if a function is even or odd can help us out with the integral of the function. But what's even more helpful is that we can actually write any function as the sum of an even and an odd function. Um, we can go about finding what each of these components are by substituting minus x into the above equation and then just using the properties of even and odd functions. So in the even case, fe of minus x will be equal to fe of x, by definition what an even function is, and then f odd, fo of minus x, will be minus f naught of fo of x, which again is the definition of an odd function. So yeah, by substituting in minus x, we get another expression. I'm going to label the top one 1 and the new one 2. By combining the two of them, we can get an expression for fe of x, the even function, which is a half of f of x plus f of minus x. And likewise, by subtracting 2 from 1, we can get the odd function f naught, fo of x, as a half f of x minus f of minus x. So if we can write a function as this odd and this even pair of functions, and we know how to find them, let's look at the integral of f of x between symmetrical bounds. We showed that if you integrate an odd function between symmetrical bounds, you'll get 0, and we'll be left with the even function in this case. So if we substitute in our definition for an even function, half f of x plus f of minus x, we can start to see why this is convenient when we're evaluating integrals. There'll be some tricky bits sometimes that by adding f of minus x will produce cancellations, and then you'll end up with something a bit more convenient to integrate. So with that in mind, let's go to the actual question. So our question was, we have an integral from 0 to pi over 2, and we've got 1 over 1 plus tan to the power of mx dx. First thing, we noticed that our bounds are not symmetrical. What I want to do is I want to shift these bounds by pi over 4. So if our function looks like this, not to say that it does, but if it looks like this, I want to shift by pi over 4 to the left. And to make sure that the integral represents the same thing, I need to shift the function by pi over 4 to the left. So to do that, uh, well, the bounds become this, and we have to have this plus pi over 4 term when we're inside the brackets. So we've shifted everything. This is our new integral. So it looks a little bit more complicated, but now we can start exploiting the even and odd things that we've just been through. So we've got f of x now in our new form with the plus pi over 4 term. We're going to use a trig identity in the blue box. So tan of a plus b is given by this fraction. I'm not going to prove it, but you can just look it up online. Yeah, by substituting in the fact that tan pi over 4 is equal to 1 and putting it into that identity, we get this expression for f of x. I'm going to multiply top and bottom by 1 minus tan x to the power of m, and then we get this expression, which looks a little bit more complicated, but we've eliminated that x plus pi over 4 term inside the argument of tan. So we've got an expression now for f of x, which is more manipulatable. This is the function that we're integrating between symmetric bounds, which means that we can change the integral to the even function of this function. If we recall, that's given by a half f of x plus f of minus x. So in order to get f e of x, we're going to need to find f of minus x. We do this by substituting minus x into the function given at the top, and we see that the denominator is the same in each case, but the numerator differs by a sign of tan of x. When we combine the two of them together and multiply by a half, we see that the numerator and the denominator is the same, equal to 1. So fe of x is equal to a half, which I think is very convenient, which is why I chose this question. But it's quite cool that we've reduced this function, which looks very complicated, into just a half. So it's worth just going back to the beginning and taking a look at the steps we've done so far. We've had an integral from 0 to pi over 2. We've wanted to think about even and odd functions to treat the problem, so we've had to move our bounds such that they become symmetric by subtracting pi over 4. To compensate for this, we've had to move the function along by pi over 4 by adding it to the argument of tan. Next, we've called the inside f of x, the function we're integrating, and we've rewritten it as the sum of an even function and an odd function. If we integrate between the bounds that we've chosen, symmetric bounds, we note that the integral of the odd function is given by 0, so we're going to be left with the even function. We found that the even function was just a half by the analysis from earlier in the video, and so we can rewrite everything as just the integral from minus pi over 4 to pi over 4 over half dx, which is much easier to do than the other thing, which gives us pi over 4, which is independent of m. So this whole complicated integral, no matter what your value of m, whether it's complex, imaginary, irrational, whatever, will always give you pi over 4 from 0 to pi over 2. So the bounds of the integral were pretty convenient, but hopefully this has been a decent example of how we can use even and odd functions to evaluate definite integrals without actually finding the integral. A neat trick that I hope might be useful to you one day.